Hi, good morning. It's really good to be here. I'm Andrew, and I'll be talking about fast prototyping DPDK apps in Containernet. I work with Comcast. So a little bit background about myself. I participate in many projects across multiple layers. I work with tools like GDB in an in-house project, working in trace points. I also worked in network layer, content-based routing in like a mobile ad hoc networks. I also worked in the cloud, key value stores. And my current project is actually about load balancing services. Actually, a lot of today's talk come from what I learned in this project. So an overview of today, what I'm going to cover. I'm going to share a little bit about what happened when we first started about planning to write network functions. And then how we came upon Containernet, what it is, what it can do, and why should I care about it. And then how we set up and ran DPDK in Containernet. Of course, a big disclaimer, we are very new to this. We first started looking into DPDK like about 8 months ago, Containernet about 6 months ago. I mean, in no way we're trying to claim that this is the best way, the only way. Is one way we found worked for us. And if you see anything glaringly like wrong that we could do better, please let us know. We look forward to learn from this community too. And at the end of today's presentation, I'll also show a short demo video of running Containernet. All right. So Comcast, I work for Comcast. We have a large network, and a bunch of us started thinking, oh wait, how about we write network functions and run on our networks? And we could use DPDK. And then everybody got really excited about it, including us. Right? We are really like looking forward to being able to change the way we do things. So we set up DPDK, like a user layer, fast packet processing. We found a framework where we could develop our functions using Rust. It's called NetBricks. So we started developing, and to generate load for testing, we actually use something called MoonGen. So to write our tests, generate traffic, and then we set up all this in a VM. And we brought this VM up in our laptops, and we could write functions. Now, once we had that, and we started writing functions, we started thinking, OK, now that I have this app, where am I going to run this? And I mean, of course, it's one thing to write a unit test to verify that the function you wrote does what you think you should do. But once it goes on to the network, how can we verify it's correct, right? That we wrote correctly. And if you do find any issues, how hard would it be to debug any issues that we found? So those questions prompt us to think, OK, what's our next step? So since we were already in a VM, the next step was, how about we just use VMs? Right? We create multiple VMs in a single host. Each host in the network will be a VM that we create in our laptop. And then we can use like a host-based networking, connect them, and leverage tools like Vagrant or VirtualBox. So that seemed a very natural next step, which we did. But of course, we also came upon some problems. One of which, the major, is that it's actually highly resource intensive whenever we spin up VMs. We tried to spin up a 10-node network, and our laptops would just grind to a screeching halt. Nothing else could be run there. And then we just realized that this would not scale very well if we tried to test over a network setting. And plus, we were experimenting with IP Anycast. And I think yesterday in my presentation, we ran into problems because we were trying to assign the same IP on 2 network interfaces. And a Vagrant and VirtualBox just had problems bringing them up. Of course, we realized later on, after long hard work, that it was an issue with a neighbor discovery protocol that we had to set up correctly or manipulate. We just didn't think it was a very safe environment after we found this. So we looked into different options. One option, of course, how about find a lab environment? I mean, you can have a dedicated space where we can run our functions, and actually a lab environment, if it's could be provided in a condition very similar to the real networks where we would be running our functions. So that's what we thought, right? But of course, we also ran into problems. It's we are application developers. We don't have keys to the kingdom of the network, even though it's Comcast. So it was very hard to make any changes. And plus, because the lab belongs to another team, like the network team, like if they, of course, if they came up with a high priority project, the resource could be preempted. So those were some problems we faced when we were exploring this lab option. And then, of course, it was remote. So many things were a little bit harder to debug. And scheduling experiments was also a little bit tricky, right? So we had multiple developers trying to write different parts, and we wanted to test and how you schedule. So all these things led us to start thinking, okay, maybe lab is also not the best place to write. So it took us a long time to make any progress in that environment. So Comcast is a large network, right? So can we run in production networks? Yeah, sure. Very, very, very. No, understandably so, right? I mean, I would never trust, if I were a network operator, I would not trust my network to some guy that says that, oh, I wrote a network function, can you run it for me? So that's when we found Containernet. So what is Containernet? The best definition is actually that Containernet is a fork of a Mininet project that supports Docker containers as a Mininet host. So this is the work where Containernet was first introduced. Then, of course, since we are doing this kind of definition, then it begs, what is Mininet? Well, Mininet, from their website, is something that can bring an instant virtual network on your laptop or other PC. So is Mininet a network emulator? Not quite. A more accurate definition would be, Mininet is a network emulation orchestration system. You can actually run a collection of hosts that belongs to the network, nodes, links, switches, and all of a single Linux kernel. Then it uses lightweight virtualization so that this single system, our laptop, will look like a complete network running the same kernel, system, and user code. So how does Mininet achieve this? What are nodes in a Mininet project? Actually, network nodes are network namespaces in Mininet. So process that belong to a specific network namespace will not have access to the host's original root network interface. So how does this work? So think about change root. When we run change root, we remove access to the host root file system. So a network namespace does the same thing, but is in the context of a network. So routing rules, IP table rules, they're all different. And then you don't have access to the same network interfaces either. So in process that start on a network namespace, we inherit the view of the namespace. So in a sense, in terms of the network aspect, we can think of them as separate hosts, right? So say we have our laptop, my computer, and then if we run this command to add namespaces, then we can create multiple namespaces. They are isolated from the root and from each other. Then the next step is to link them. How can we link these network namespaces? Well, in Mininet, we use something it's called a virtual Ethernet VF interface pairs. Right? They act as tunnels. They can link to network namespaces. They're like a cable that can connect to like a host together. So a packet that goes out from one end gets received by the other. So they are always created in pairs. So this is the command that you can create a VF pair. And we can use this command, set, IP link set, and move them into their proper network namespaces. And then you can establish connectivity between these two network namespaces. The final piece of the puzzle then is switches. Right? How does Mininet emulate a switch? Well, it actually leverages OpenVSwitch, run in kernel space, connect to an OpenFlow reference controller. So what does this mean? This means that the switches that Mininet instantiates act like Ethernet learning switch. So actually, we have everything then. We have a network name. We have the node. We have something that can emulate a node. We have something that can emulate a cable linking. And we can have a switch. Right? You can use that to connect multiple hosts. So, and then, this is just some observation. By default, switches in Mininet, they live in the host network namespace, but you can move them to their own individual network namespaces if you need it. So, how does this look in our diagram? Like, say we have this namespace, and they would be connected to the switch, and the controller would be the one dictating how packet processing happens in the switch, right? So, for all practical purposes, like we mentioned, the switch would act like an Ethernet learning switch. So these are the elements that allow Mininet to emulate a network. And it wraps everything around a Python API for us. So this is so the commands used to create the switch, the VF pairs, namespace, they're all wrapped around Python. And we can actually, later we'll see that you can actually execute commands in each host. Like you can SSH into a host, like you do to a remote node, but having the advantage of everything being in your laptop. So this is an example that actually is in the Containernet repo, right? So we're going to go over this just to see, get a feel of how the Python script for setting up a Mininet network emulation would look like. So initially, right, so you import all the elements that you need, like any Python script. You can actually, there is a log level that you can use for printing out debug information. Then you create the Containernet object. You notice that we can pass the controller. And without any argument, it's the default controller, right? So it's the controller that when we add a switch, the switch will act like Ethernet learning switch. Then we add the controller to the network, and we can start adding hosts. So we add Docker container, and we can pass the image. We can set up the IP address, give it a name, D1, D2. So all this is part of the Python API. After we add in the nodes, we can add the switches. And now we can add the links, how they connect to each other. Notice that the adding link can also support adding different delay characteristics or even bandwidth for the link. So this is all supported in Mininet. You can create a very realistic network setup. Then we can start the emulation. Then you can SSH into the nodes. You can ask them to do things so in this example, we execute a ping command from the host D1 to D2. This is via the Python API, but this next CLI will create a prompt from where we can actually run commands manually, interactively. We're going to see this later, right? So then this is how we can set up. That's Mininet, as we said, performance emulation, and that's how we set up the network. We can start traffic sources, routing software, and any software that we write, because of emulation, it will execute as is, interacting with the real network stack at wall clock speed. So of course, it has its advantage, like when TCP BBR was introduced, released as a Linux model, I think, source, it could be run on Mininet. You didn't have to wait for the port to any simulator. You could just run directly on Mininet. But of course, because it's an emulation, it's limited by the underlying hardware resources. If your hardware cannot push packet faster than 10 gigabits per second, you cannot emulate a link with that capacity. And of course, it's also wall clock speed. You cannot emulate, if you want to emulate 5 hours of traffic, you have to run 5 hours. It's not like a simulator in which you can run, simulate, say, if your mod is accurate, you can simulate I don't know, a month in a few hours, right? So this is some restrictions and advantages and pros and cons. And it's also Linux only. And of course, it uses Ethernet links. So for us, that was not a problem. So we thought that this was a very good tool for us to start writing DPDK apps and deploy them and running on them, right? So DPDK, so we had to learn how to set up DPDK to run Containernet. Now, at this stage, we're still very focused on making sure that what we write is correct. We're not focusing on performance. Yeah, for sure, all this virtualization will impact the performance of DPDK, but we are trying to ensure that the functions we wrote, they have correct behavior as expected, right? So in our setup, we use this environment abstraction layer definition for Linux, and we are using the AF packet PMD. So AF packet is actually is a raw socket in the Linux kernel. Essentially, if an application is grabbing packets from the raw socket, the AF packet socket, the more correct is that it ends up grabbing an Ethernet frame. It bypasses the entire TCP/IP networking stack of the Linux kernel. So that AF packet PMD is what we're using to run DPDK apps in Containernet. So this, for for our load test, the packet generator. These are the config options that we passed. And in NetBricks, similarly, it allows this kind of configuration options to pass an AF packet PMD. So another thing that we found was that because we are running multiple DPDK apps in the same, like a Linux laptop, right? So Linux machine, we had to give them individual names, like based on host, for instance. But this was not a problem, so we were able to execute that. Then, some caveats, right? Network is isolated from each other, but they share the same file system. So any config files, make sure that they have a unique path. Should make sure that, that there's no conflict. Otherwise, if you just end up doing like a name that's shared across multiple hosts, that it might just overwrite. Mininet uses VF pair, virtual Ethernet face. These days, a lot of TCP checksum segmentations are offloaded to the hardware. And of course, a VF pair will not do that for us. So we had to disable TCP checksum. So you had to rely on, for our DPDK apps, we wrote our own checksums. And for like other hosts in the network, we had to disable TCP checksum offloading. Right? Then, but after all this, we had access to all the hosts, all the links in the network, and we could run most tools on it. So we were able to run Wireshark in the switches, TCP dump, Dropwatch. Like we had all the tools in our favor. And we could run real network protocols like BGP. We can control forwarding rules, IP tables. Everything was in our control. So that was really crucial for us when we start developing. When we are application developers, there are many networking things we have no idea. So it was very, very helpful for us to have access so that we can, every one of us, we are a small team, 4 people, but every one of us could run and check and find out what was going on. So I'm going to go over to I'm going to start a video. I just wanted to show the topology of the video that, of the script that we're trying to create is the 10-node network that I had mentioned previously. So essentially, these are 2 router switches. These are switches. All these are Docker containers. The BGP nodes, they run Go BGP container. They will peer with the router, and they will advertise routes or remove routes. So to show that, yeah, Containernet, you can just really act like a real network, can add routes, remove routes. And the routes that they are advertising is this. They will say that if any client node needs to reach this IP address to start with 2001, the router would forward to the OG node that is closest to it, right? So this BGP node would say, okay, if your West client comes to you and wants to go to this IP address, then you will forward to this OG West node. Now, OG West is where we wrote our DPDK app. So for the purpose of this demo, this will simply forward the packet to the agent. This agent, we have actually we have an eBPF filter running there that will forward the packet to the web server that is running. And when the web server's response comes back, the eBPF filter will redirect the packet back to the client directly. So this is actually the loop that we have developed and which we're going to try to show in this short video. Okay. Okay, so these 2 terminals are just like shells in our Vagrant VM. And when we start the emulation, right, so you just run this Python, just call Python and pass the script. And once the script is executed, you will bring up all the nodes, and it will say, okay, what directories need to be mounted, what is the image, and see it can configure, like, say, these many nodes. And it started the controller, and for the routers, we are running Zebra and PGPD, right, to simulate a router behavior. So the scripts that we're using to delete and add route are shown in this screen, right? So it's essentially a Docker container, it's a Docker command accessing the Go BGP to say you can add or delete routes, okay? So I'm just showing again the topology. And we can see that here, we started the BGP process in the Go BGP, BGP nodes, and they are trying to peer with the routers. I mean, it will sometimes take a few times, but once it connects, it will announce the route. So from this moment, any client going to the router forgot which one it is. Okay, fine, whatever. So it completed, both completed. So it's supposed to, client requesting anything from that address, we'll just go there. So this is the CLI that I had mentioned before. We can check what nodes exist, what are the links, right? So we can understand the topology. And you can create X terms that will be executed inside each host. Here, I brought 3 X terms, one in the router, and one on the client, and one on the OG node. So out of the router X term, we can bring up Wireshark. So I'm going to bring up 2. One, to monitor the interface that's connected to the router, OG node, and one, to monitor the interface that's connected to the client. So this bottom one would be, so based on the link interface, I know that this bottom one, okay, sorry. So the top one is the one that will be the client one, and the bottom one is the router one. Now, our OG process already started, and they're logging to a file. I'm going to change so that you log it to the console, right? So you can see what's going on happening. So see, so the DPDK app got started. It was able to instantiate the EAL, right? Now, from the client, it will try to access that IP anycast address. So we have a web server running, bound to that IP address in each of the agent nodes. So once it completes, it says here, web server east. We can see that the top one, the client, is all green. Wireshark thinks that's a perfect TCP transaction, but of course the bottom one, because we are forwarding, it does not understand the TCP protocol. So if you run traceroute here on this client node, okay, we are dropping ICMP packets, so we cannot see the whole thing completed, but we can see there were 2 hops, right? So now we're going to try to delete the route. We delete it from the east side. What we should see is that the client will then automatically access, will quote unquote, fail over to the west, which happens. And you can see that the transaction happened correctly, the TCP transaction fine, but the bottom one, nothing happened. And when we run traceroute, you can see 3 hops instead of 2. Right? So what happens if we restore the route? Then we should restore to the original condition. All right? So this is what should happen. We add the route back, and we go, and we say the curl, the same IP address, and we get back to east. And both, we can see the packets crossing the interface as expected, and traceroute restored to having only 2 hops. Right? So clearly, in Containernet, we can definitely simulate all the aspects of the network. We can inject routes, remove routes. We can do a setup the topology we want. We can run the software we want. We can monitor everything. This was extremely helpful. I cannot emphasize this enough. Extremely helpful for us to debug the conditions we found, what was happening, why this didn't work. So yeah, so that's why we felt that this enabled us to create a prototype much faster than we stuck with the VM model or the lab model. Right? So to summarize, we started writing network functions, and we select this set of tools. DPDK, NetBricks, MoonGen. And as we were looking for an environment where it could develop, we looked up about VMs, labs, production networks. None of them was truly suitable for us, but we were able to find Containernet, which was scalable. Actually, Mininet claims that they were able to create 4,000 hosts in a laptop. So that's a claim. It's scalable, configurable, we can configure each host individually, independently, and actually run real software stack. We were running Zebra, Quagga, PGPD, or GoBGP, everything, it's the real software that would be interacting in a lab or final production network. And the great bond is we had access to everything in the network. We could see everything happening, and we could, that would be very helpful for us to have the feedback cycle to change and correct, right? So thank you very much. This is the, if you cannot grab me later, and if you would like to ask questions, feel free to contact me on LinkedIn and ask any questions, right? So I think that's it. Thank you. And any questions?
One quick question. Any reason you chose MoonGen over PacketGen or what's the one at VPP, Fido? T-Rex, right, for a packet generator. Anything unique about MoonGen, or just that's what you're familiar with?
No, that was one thing that we found, that like we said, we're just very new to this field. We didn't know better back then, so we just picked MoonGen. I think the Lua scripting also was helpful because some team members were familiar with Lua, so that was
Okay. Have you ever done any work with route bricks?
No, we haven't.
Okay. I don't know how familiar is with NetBricks, but when you said NetBricks, that's where my brain went. But
I'm sorry, then
router bricks?
router bricks? No, I haven't.
Okay,
Yeah.
thank you.
Yeah, okay.
Using the AF packet, and the AF packet is very low performance,
Right.
and also you are using all the kernel network stacks. So why are you using DPDK here in container?
No, I mean, of course, the eventual move to a real network, we will not be using AF packet, but AF packet is the PMD that we can use to run the DPDK app in the Containernet. And the advantage of Containernet, to our point of view, was that it enabled us to run an app in an emulated network environment. I mean, that's all. I mean, of course, we are trying to move our app to, so we are actually trying to move to the real network. Then we have to change the PMD. So that's one thing.
Yes, so when you move to the real network, will you use DPDK, or you are using the kernel interface?
No, we'll be using DPDK. That's the plan.
Okay.
I guess, I'm not sure, so I think we are application developers, we are very new, so we wanted to have a place where we can run our DPDK app over a emulated network where we can see how things are happening. So the main point is that we want to make sure that the network functions that we wrote would act the way we intended them to, right? DPDK, we are hopefully that when we are moving to, when we put in a new PMD, then they will act the same.
Yeah, you mentioned new PMD. So what kind of new PMD? Is it a NIC PMD or the virtual device PMD?
So that's something that we are looking right now. But for now, I think we have been using the virtual device PMD.
Yeah, thanks for virtual device. I'm not sure how much performance gains you can get from DPDK.
Right. I mean, there is the talk. We are in our cloud team to do the bypass. I forgot the exact name. Yeah, like I said, we are very new to this.
Okay. Thank you.
Yeah, welcome.
Okay. Thanks, Andrew.
Oh, sure.
I have a question related with the container communication, because you mentioned that container to container still need to go to the kernel for the stack, right? Mm-hmm. So it looks like it's not very efficient, because from my understanding, some projects we are trying to get a shortcut from container to container so that it will be more quicker for the communication, and the performance will be increased to bypass the kernel, just to go from the user space to user space.
Right. I mean, I think, yeah. I mean, I'm not sure if there are projects out there that can emulate the whole network this way. I'm sure that will be more efficient, but
yeah.
I mean, we are just trying to run in an emulated network environment. Like I said, we were not trying to focus on performance. We were trying to focus on the correctness of the function we wrote. Yeah.
Okay. Thank you.
All right. Thank you.